announce the next speaker, which is Pavel Sulimov. So welcome on stage. A PhD in computer science and is currently a quantum machine learning researcher at ZHAV. So this is the Zurich School of Applied Science. Yes, I hope you already know what machine learning is.
Do you have like these?
And I guess you also know what quantum computers are.
Let's go! Whoa! Yeah! Thank you. Yeah, that's fine. Let's see if you're so much excited about the talk, and then you give the same kind of applause if you like it, okay? Let's do it like this. So, basically, already very nice talks today, yeah? And before, these were guys from Quantco. Maybe time for quantum, yeah? Exactly, very nice switch. So let's go strictly to quantum. So, we all know classical bits, yeah? The one that they use in the computers. And now imagine that there is a bit that has not yet decided if he's 0 or 1. And he just has like the internal probability, like what it is closer to. So this stuff is called the block sphere. And then imagine that our bit is sitting somewhere on it. And finally, we have like the two poles, like the north and south pole. And basically, it sits somewhere like in between on the surface. And when we say like, stop, yeah? He should be switched either to 0 or to 1. And this is the point where he's going to become kind of a classical bit. And the closer it is to the pole, let's say of 0, the more is the probability that it's finally going to be measured as 0. We call this measurement. Yeah? And you might feel that there is something already very close about, let's say, machine learning, yeah? That there is something, you know, like in machine learning, we love things to be between 0 and 1, yeah? It exactly saves us from some unexpected things. Also, there is the stuff that we can tweak something, yeah? You remember, we tweak weights in neural networks. Okay, boom, let's then do quantum machine learning, yeah? Very obvious. But in fact, it all started with the Google showing the stuff that is called quantum supremacy. So it has shown that quantum algorithms on the particular tasks can work faster, exponentially faster than the classical algorithms. And for the algorithm itself, when we are not talking about the machine learning, yeah, for example, we are talking about the quantum break of the encryption, yeah? This has the internal property of quantum, which is parallelism. So it means that due to our, let's say, qubit, yeah, we call it quantum bit qubits, due to our qubit being like somewhere between 0 and 1, physicists are saying that it is like in the same positions at the same time. So like it could be whatever, yeah? So like it means that if we have many qubits, yeah, we can have all the possible combinations of them. Basically, this is how it works. And this is about quantum algorithms, yeah? So I'm gonna talk a little bit in details later, but quantum machine learning is a specific cool stuff. So the qubits, they have like a gorgeous property, except from parallelism. So it means that before we measure them and say like, stop, yeah, they're like both 0 and 1 at the same time, they can also be entangled. So it means that they just get a little talk in advance and say that, okay, let's remember, if you are 0, I'm 1, yeah? Then if you are 1, I'm also 1, or whatever. So I mean that they have kind of, I mean, it's a little bit of philosophy to some extent, yeah? So this is more like a spiritual sense today, yeah? So we are more talking about some stuff that does not exist in practice, yeah? Because internally there are also complex numbers, etc., etc. But basically what we need to know is that this kind of idea of entanglement, meaning that these qubits, they can talk to each other in advance and then have like some complicated dependencies, it means that we can create, let's say, the simpler neural networks if they are based on this kind of principle, that there is an entanglement, and if we create a lot of entanglements, then basically we can have like the minimum number of parameters in our network, and this is like the example of network, yeah? So it's almost like the machine learning, like neural network, but these are like the inputs are these between 0 and 1, yeah, some stuff encoded. And basically, this gives like the potential for creating, let's say, like a mini ChatGPT, quantum ChatGPT, that's gonna like be trained immediately and basically having the same kind of quality. But this is tomorrow, yeah? Today it's a little bit different. Today it's still about, let's say, using more these quantum machine learning and general quantum algorithms for some, let's say, simulations of the processes from the nature. What I mean by this is basically, for example, quantum chemistry. So, and I would say now this is the most perspective trend that I see in the field, I would say. So it means that imagine that we can create absolutely new variables of molecules, absolutely new new concepts of molecules. That's going to be, for example, I don't know, the healing of cancer, or I don't know, like healing us from everything, from diabetes, from whatever stuff. So you see, I'm very much excited about saving the world. But as I said, tomorrow, yeah, tomorrow. So today is just a little bit simpler. But, you know, you have seen already there is a lot of maths and like even machine learning. Then say, man, come on, where is the Python? Exactly, yeah, so here is Python comes. So because when guys were developing the packages that need to work with the data with quantum computers, they immediately choose Python as the main language. And these are like two main things. So the left one, it is called PennyLane. The right one is called Qiskit. We're gonna start with Qiskit. Qiskit is by IBM, yeah, IBM. Big guys, and they have created this stuff, I think 2019 or something like this, and basically it was created in order to run the programs on their quantum computers. Because you can imagine IBM are big and rich guys, yeah? So they have good quantum computers, and as Rafael asked already, someone already run it, yeah? Someone gets registered, run it for free, and you can do this. You're gonna have a link in today's presentation in order to run it for free. Could you imagine you running the program on quantum computer, on a real quantum computer, yeah? It's incredible, but you can do it today, yeah? I can tell you later today, yeah, how to do it. Just come to me, that's okay. And the good thing about this Qiskit is that IBM, knowing its own computers, how they work, they were able to create the internal optimizers. Because when you are, let's say, creating your quantum neural network, and you say, I want this entanglement be here, this one rotated like this, boom, 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 so you're creating some stuff. Behind the scenes, it works absolutely differently. So in order to run this program that you have created in your mind, yeah, IBM needs to make so many shufflings and attachments on their computers so that only they know how to do it. That's why they keep this, I mean, it's not a secret, but it is very prone to the computer where you are running. So your program very much depends on where you run it. And the talk was called like Qiskit 1 point whatever versus PennyLane 0 point whatever. So Qiskit finally got released, the good stable version February this year, and it is very poor backward compatible. So I mean, like now half of the code that was before doesn't work. And so this is kind of, let's say, the main issue that happens with that, except from this gorgeous package, yeah, IBM is a gorgeous company, but this backward compatibility is a problem. And it has even its own, let's say, attachments and different kind of integration with PyTorch, TensorFlow, etc. But now again, due to all these changes, it needs to be double-proofed. So I would recommend you to think twice before you do it. Okay? Good things. A little bit of good stuff. Or let's say interesting stuff that is good to know. That if you search, if you start, for example, today, later with the Qiskit, and you have some bugs or problems, in the internet, you're going to find no answer. If you go to Stack Exchange or Stack Overflow or whatever, you're going to find that the last answers are from 2019. What has happened? Qiskit decided to put everything to Slack. So that's why like the latest bugs, discussions, etc., they're in Slack. I would find it a little bit questionable, yeah, taking into account that then you need to have a Slack account registration, etc., but it is as it is. Like the good thing, except from this, is that they have a gorgeous YouTube channel. Absolutely great one. So they have like many, many funny videos, like 1-minute videos, 1-hour videos, 1-day videos. So like basically all about quantum that you need to know. And I would say it's more for lazy learners because really they explain everything by part. So you can do it. More to say, yeah, if you get registered at the IBM cluster, the link is in the description, yeah, then basically what you can do, you can create your own circuit that I was showing you, yeah, it means that basically you are showing that these are qubits, these are entangled, these are rotated, etc., and you can just do it without programming. You can exactly do it as it is shown on the left, so you basically create your circuit, this is called composer, yeah. And before, it was even the case that IBM was producing then the code for you, and you could have then run it on their cluster in a Jupyter notebook. It was great, but then somebody, I would say not good guys, understood that they can use it for Bitcoin mining. That's why now there is no more lab with Jupyter notebooks from IBM, and this is a big pity. Yeah, so that's why unfortunately we don't have this possibility, but it was before, it was great, yeah? And as I said, registering and imagine 100 plus qubits machine. In fact, I would say it is 133 machine, and you would have like a free access for a couple of seconds. And trust me, these would be the best seconds of your life, or at least of today's day. So just, I mean, do it. You would then say thanks to me. This is a Qiskit. But there is a competitor. You know, usually when you're creating some good stuff, there is also another guy who wants to get the market. Yeah, like McDonald's and Burger King, yeah, for example. So this is like Qiskit and PennyLane. And maybe PennyLane is more about these fire-burned buns and burgers. Because it was created a little bit earlier than Qiskit. I think it was 1 year earlier. And it was created specifically for quantum, I would say, in deep learning, not just machine learning. It was created for quantum deep learning. So it was exactly created in order to support the functions of the quantum derivatives. I will not go too deep into quantum derivatives. If you want, you can go into this article that is there cited. But basically, the thing is that in quantum neural networks, you can take the same kind of the autograd idea that is, let's say, in PyTorch. Yeah. So, and I find it absolutely gorgeous. So it means that you can take like your usual neural network, rewrite it in a quantum way, and still the optimization process would be done the same kind of the same way as it was before. And the good thing is that even though it is version 0.38, yeah, they do not claim that they have version 1, 2, whatever, 50. It is quite stable. It is backward compatible. This is what I like there. But PennyLane doesn't have its machines. This is a big problem for them. So that's why they need to sell it to people so that, come on, use now PennyLane with, for example, IBM machines. So that's why they have created like a special integrator that is called PennyLane Qiskit. And via it, they are selling it. And you can even read it here, yeah? They're saying that PennyLane is a cross-platform Python library, boom, 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 boom. Qiskit, open source framework. Yeah, so just something just that you can use in order to access IBM machines. But basically, you can do it, and if you would like to do it, these are the links. Interesting stuff is that this screenshot I have made a year ago for the students in university at Quantum course, and it was recently, and it was there written that demo currently doesn't work because of Qiskit again changed something. I checked this link yesterday, it works now. So follow the link and try it out. So this is gonna be interesting experience. And just to tell you what I like a little bit more, let's say here, is that they have kind of, you know, PyTorch has this discuss.pytorch website. Here they have discuss PennyLane. So it means they do not have Slack. So you can just freely go there and see the answers to the questions that you want. Also, they have nice tutorials, and I would say pictures are so nice. You know, they're so warm. So I mean, Qiskit is good, yeah, but they do not have soul in their pictures. If you go to PennyLane, this is like as if Granny has drawn these pictures, yeah. So you want to stay with these pictures. You want to stay with PennyLane, and they have more to say code books. Basically, they have kind of the same examples of programs as it is on lead code, code wars, whatever. So it is absolutely the same style, and you can run the code there, and it is gorgeous. So, and obviously a better integration with frameworks because it is stable and cool. Now, where to apply it, yeah, because it was announced. I told you, no Python code is going to be presented, sorry, on the links, but there are going to be like the example of applications. If you don't know yet the RSA encryption algorithm, this is just for you, a little formula. Yeah, you can quickly go through it. Basically, this is how it works. For those of you who want to get like a little bit more brief introduction, I can tell you that it works on the idea that I can tell you that 15, it is 3 multiplied by 5, but I cannot tell you that 2 to the power 100 minus 1, what are these 2 prime numbers that are multiplied in order to get this particular number. And it's not me stupid, yeah? Machine can also do it only in a very, very non-reasonable time. So basically, this is the idea of this RSA algorithm, and in order not to go too deep into mathematics, just a little bit of quantum Fourier transformations. And there are nice links to the YouTube videos where you can go more into the physics that is used behind. So basically, there is a guy who is called Shor, and then at some point he was sitting and understood that I know how to use this idea of quantum parallelism in order to break this conundrum. And basically, he suggested this algorithm that, in fact, can solve this problem on quantum algorithm with quantum computer much faster than in a classical way, because classical way is just going number by number. It's going to be like 3 multiplied by 5. It's not yet 2 to the power 100. Okay, let's continue, yeah? And so this is almost how it works, yeah, in classical way. In quantum, it works much smarter. I would recommend you to go through these videos. Very nice guy. I think he talks for 9 minutes, and I had to rewatch it through whole the day, these 9 minutes on a loop in order to understand what it is about. So just if you get a little bit depressed, then you can watch it. So, but then there are also like the solutions, yeah, already implemented of the Shor's algorithm. And I would say, again, on PennyLane, I like the fact that it is implemented in these code books. You can exactly take this link. I have checked it, it works, and run it. On Qiskit, there is the thread on Stack Exchange there where people are asking why Shor algorithms doesn't work anymore on Qiskit. And there is a good answer saying like what should be changed in order to be compatible with the new version. But I also tried it, it works. So that's why I use this link. So basically it's a little bit more complicated to be done, but basically you take the Jupyter notebook from Qiskit and then run it. But without nice pictures from Granny, yeah, as I said. Also, those of you who like money, yeah, I think many people love money, at least I love. So I would share with you a little secret. So there is also the financial aspect in the quantum computations. Basically, if you know, there is like such a derivative in the financial instruments that is called the option. And in fact, this is kind of the gambling. This is betting on where your stock's gonna go, and then you kind of buy the rights to either then sell them or to buy them, depending if you guess or you don't guess. And you pay like a little premium for this. And basically there is like an old, well-known formula, and there are many other formulas, like Black-Scholes model, for example, yeah, that tells you how you need to calculate, depending on how the volatile market is, in order to get, let's say, the right profit. But there is a better way now to do it with these quantum things. So basically, there are quantum guns. Yeah, could you imagine? There are usual guns, yeah, generative adversarial network, that now nobody's interested anymore because there are diffusion models, etc., etc. But quantum guns, this is like the top of the quantum neural networks. Meanwhile, because finally, I think only recently people implemented like all the possible combinations of generative adversarial networks. And one of them exactly suggests you to create these exotic, absolutely unbelievable prices for the options. So go through this link. Again, I checked the code, it works, and then write to me if you made money. Basically, don't write to me if you didn't. I mean, if you want to have like the exact comparison, because you know, now I'm just giving my biased opinion saying that, okay, PennyLane is better here, Qiskit is better here. There is like the experimental comparison that is quite recent. So it is like the 12th of June this year of Qiskit and PennyLane on the, in fact, it was like the quantum support vector machines, basically, because there is like the idea of quantum kernel, very interesting stuff. But when I opened it from the home internet. I don't have the university subscription. Jesus Christ, 25 francs for this article. Come on, no. I mean, this is the most important here because the article itself doesn't work. I read it yesterday. Just don't buy it. Meanwhile, you are here on the internet. If you see the subscription, you can download it. Otherwise, do not do it because like they basically say that both can do it. Very nice, yeah. So, and this would be kind of the general outcome of this presentation. That yes, I would say that both Qiskit and PennyLane can do many stuff about quantum machine learning. It is more the case, let's say, what suits you more if you want like to have this program running faster, for example, then it's perhaps like a Qiskit, or if you want like to have a better integration with PyTorch, if you are a fan of PyTorch, then I would definitely recommend to go for the PennyLane, because there it is like the smoother optimization integration. And just to say what are still the challenges, yeah, because I'm telling you, yeah, use Qiskit, use PennyLane. In fact, there are a lot of problems around it, yeah? That's why today it's the only talk in quantum, yeah? Otherwise, I think there are going to be a lot of quantum machine learning talks of people who are in it. basically loading data from the classical format to quantum, it takes quite a time. Then, still, this number of qubits, I told you about 133, yeah? IBM has the idea to make, by the end of next year, 2025, 1,000 qubit machine publicly available, which I do not believe it at all, because currently it is 133, and they internally have 433. So I would say still, there is like a lot of stuff to get improved. And also the price. The price is amazing, $1.6 per second, yeah? That's why I told you, these would be like the gorgeous seconds of your life. So these would be the most expensive seconds of your life. Honestly, these are like only like the main limitations that I enumerate here. There are many more. That's why, basically, you can already start with it, but I would say that with not too much rush. What you can do, you can try such a called hybrid classical quantum neural network. It means, let's say that you have like a big neural network that is slowly converging, yeah? So like your layers become like thinner and thinner, like, yeah, less number of neurons. And at some point where the number of neurons in the layer is already small enough in order to get, to be fed into the quantum machine from IBM. Good, you are saying, okay, I'm switching, yeah, because there is this integration of the derivative flow. That's why you are thinking, for example, you have like the layer of 50 neurons. You are saying, good, these are my 50 qubits. Now I put it to quantum computer, and it's gonna get for me more complicated dependencies. On practice, it occurs that still the scale that we need is not yet good. I'm gonna discuss it on the next slide. But for me, you know, it more feels like with classical neural networks. Because, you know, classical neural networks were developed quite a time ago, yeah? Then a little bit more of algorithms, then nothing. Then GPU appeared, boom, yeah, a lot of algorithms. So I think here is going to be kind of the same. So we need to continue developing these quantum algorithms. We need to get improvement of these Python APIs and packages and basically wait, yeah? You know, like Geoffrey Hinton did. He was waiting, and do you know what happened this year? Exactly, yes, so finally, Nobel Prize. I think this is kind of the same idea. Just wait a little bit, and your Nobel Prize is gonna come. So just at some point in the future, maybe you're still gonna be alive if you're lucky. Then a little bit of shameless self-promotion, what I did for my Nobel Prize. So for my Nobel Prize, recently we have done this quantum machine learning for the cardinality estimations in the queries, you know, when you are making the filters on the queries, like in SQL, yeah, select star from whatever, where, whatever, I don't know, year is less than 1,000. So there, in order to run these queries faster, you need to make this kind of estimation of what like part going to be left, and then you have like, if you, for example, join 10 tables or even more, you have a lot of, let's say, functional dependencies between these tables, and we have tried to model it exactly with the quantum machine learning with these entanglements. And it worked, but again, on a small scale. So when we try to scale it up, it occurs that we need many more qubits in order to scale it for the real databases. So that's why it means that people can check it, that it works or it doesn't work. I decided to switch to the stuff that people cannot change. These are galaxies. So galaxies are great. There is a lot of data on galaxies, and in fact, one of the hottest topic now in the cosmos, yeah, in the analysis of galaxies is the galaxies classification. So basically, we have photos of galaxies, we have the data of galaxies, like the radiation that comes from there, and there you can try to exactly classify what type of galaxy we see. And we have found out that exactly there is this kind of a little bit of natural data that, let's say, fits this idea of the quantum Fourier transformations, and it means that it could be then modeled much better with the quantum machine learning than with the classical one. So I would say that I bet more on this. If I would be suggested like an option to put on databases or on galaxies, I would say galaxies is my choice. And in order to get you even more involved, even more interesting, just imagine, I was preparing this talk. The previous slide was already the last one. Then what I do, 2 days ago, yeah, I open, I see, oh gosh, Google Quantum AI, and Google Quantum AI is gorgeous. They sit in San Francisco, enjoy their life, and invest quite a lot into the quantum technology. So basically now they invest in the new neural atom quantum computers. I have no idea how they work, but sounds cool. Yeah, neural atom quantum computer, boom. Yeah, then a little bit earlier, like 4 days ago, I read Chinese researchers claim breakthrough in exactly this RSA encryption, yeah? The thing is that what they have done, they have broken the RSA code, which is encoded with 50 bits encoding. Maybe you know that now the current RSAs, they're like 2048 bits encoding, yeah? That's why I would, let's say, hold on with breakthrough. So like from 50 exactly to 2000, there is still a space. But the good thing is that the algorithm itself is pretty nice done. And exactly, as I say, it's just a matter of time. But according to the calculations for the true decryption, we would need roughly 6,000 qubits. Yeah, you remember I told you now it is 133. IBM wants next year 1,000, which I'm very suspicious about, and then 6,000. Yeah, so we'll wait. And this was 4 days ago. So I mean, like this stuff is coming over everywhere around, and you just need to like touch your pulse and see if you keep up with this. But basically, I would say, I don't know if I'm still on time. Oh, I think I'm perfect on time, even taking into account that we started later. So then I want to thank you all. And this is like the quantum thank you. So like with probability 50. So like to half of you, thank you. To others, big thanks. Yeah, thank you guys. Thank you.
Yes, thanks a lot. Even with like a bit of trouble with
No problem.
no problem there. Are there questions in the room? Like
you need time to digest. It's okay. I mean,
yeah,
or you already digested.
Here, nonetheless.
Okay, good. Very nice digestive system. Let's go.
Hi, thank you for your energetic presentation.
Thank you.
Regarding the quantum supremacy that will claim to show in 2019, didn't IBM actually came up with a classical algorithm later that solved the same problem on a classical computer in like a few days and then rejected the claim actually again?
That's good. So exactly the link that I'm showing, it is already the updated version where Google says like, okay, yes, IBM did it, but now we have like another algorithm that is already beating IBM. Yeah, so that's fine.
Okay.
Things are very fast, you see, very fastly changing. Exactly. We need to keep in touch with it.
There's a question over there by Timon.
Yeah, please.
I hope my colleagues don't kick me out for that question, but did you try out the .NET framework Q# for quantum programming? Mm-hmm. And what do you think about in comparison to the Python libraries?
No. I can tell you honestly that I didn't try. I know that it exists, but to the best of my knowledge, it doesn't yet have that good compatibility, but definitely I think it deserves to try it out. So as I said, Python is the mainstream, yeah, but there are exactly like the other things. Even there is something to my best knowledge with Java. So I mean, like, I would never think about it. But yeah, so I mean, honestly, I didn't try. I know people who tried, but since then I never seen them. So yeah.
So are there more questions? I see.
There.
Several. Can you keep your hands up? Or
yeah, so to the best of my knowledge, the quantum machines that IBM has are still noisy qubits, right? So do the libraries have any facilities of dealing with that?
Mm-hmm. Yeah, good question. And yeah, I think I should have maybe noticed it. We can exactly discuss with you later on. But noisy was like now our colleague is talking about. It means that basically imagine that you want to create entanglements between qubits. But there is a lot of other interesting stuff. So imagine that you have a dog puppy, yeah, that is sniffing everything around. So basically now quantum computers, they are like this. So these two guys, they need to be entangled, but they are sniffing around the other stuff happening. And in fact, they just finally do not get this entanglement. So this is exactly the noisiness stuff, the internal noisiness. So how I would say that IBM has solved this, not solved this problem yet, but they made like a great improvement in terms of not the machines itself, but then the error correction algorithms. So now they have a lot of on top of error correction algorithms, and if you let it run a little bit longer, so inside the Qiskit, you can choose exactly the parameter that helps you to fight against the errors, the quantum errors. And basically, if you let it run longer, it would give you much more stable results. Yeah, this is how they do.
all right, one last question over there.
Thanks for the talk. As an expert, as you are, you're walking around, right? And as an expert, you see the problems you have your mind on anywhere. So what would be perfectly problems you see in daily life where you think that is a quantum problem to solve?
Okay, daily life, I mean, depends who you are. So, I mean, for example, if you work in a lab with the NMR data, like the magnet resonance therapy data, then I would say for you, this would be now the best application, because there I see like the majority of work going to this direction, because the NMR data, this magnetic resonance, it has the quantum nature itself of the Fourier, quantum Fourier transformation data. And basically, in order to process it classically, we make the additional processing of converting it from quantum data to the classical one. And what is done now, and I think soon it's going to be exactly the breakthrough, not the Chinese breakthrough in the RSA, but the true breakthrough, where people are going to exactly get the right reading of these initial quantum data and then pass it through the quantum algorithms and extract like the accurate solutions. I would say there is the main focus now.
Thanks.
Thank you.
All right. Thanks a lot. And